when I communicate science to someone who doesn't have background expertise, they're not dumber than me. This idea that we said we are dumbing down in order for people to understand, they're not dumber than me. They just haven't had the benefit of years of dedicated thinking about this stuff that I have. Getting an idea across in a way that I think they can understand. Sure, I'm going to probably leaving out some of the details of the algebraic derivation that are not important in getting the concept across, but it gives me genuine pleasure to see that penny drop, the light bulb come, and we say, oh, I see now. I get the same sort of tingle, enjoyment of someone understanding something that I've explained that I got when I first learned that.
Today, you are all in for a treat as we speak to Professor Jim Al-Khalili, who is a fellow of the Royal Society, a quantum physicist, and holder of the University of Surrey Distinguished Chair, as well as a personal chair in physics. How many chairs can you have? You've got a university chair, a personal chair, and the public engagement of science.
Yeah, I've got a whole three-piece suite, I say.
You're like a one-man IKEA.
It's exactly.
I am going to try to be mindful of your time because I know it's very gracious of you to spend any time here, but we have a new book that's coming out called The Joy of Science. So I want to start off by doing what you're told never to do in life, which is to judge a book by its cover. So Jim, tell me, what is the origin of this book's title, subtitle, and the awesome cover design as well?
I had a whole list of different titles that I had suggested to my publishers, Princeton University Press. And it was about, rationalism, the scientific method, and none of them really sort of resonated or sort of captured the imagination. And then my editor at Princeton suggested The Joy of Science. Because, it is a celebration of why science is so important, why we scientists do what we do, how it gives us this a better understanding and empowerment because we can understand more about how the world is, enlightenment over ignorance. But it's also a book about how we do science, the scientific method, and the fact that if we could use some of the techniques that we use in science, when science is done properly, in daily life, I think it would make everyone the happier. The idea of, the importance of doubt and uncertainty, the importance of examining your evidence, being prepared to change your mind. So it was 8 lessons from the scientific method. So that's one of the reasons why you have sort of the letter 8, 2 circles on the cover. And the other is at the very beginning, I use an example. I'm not the first author to do this. People like Carl Sagan certainly use it, talking about the beauty of the rainbow and why, when the poet Keats criticizes Newton by saying, you've destroyed that. Exactly. The breaking light into its prismatic colors somehow.
Unweaving the rainbow.
And you destroy the beauty and the poetry of it. And rubbish, the Feynman talks about this very eloquently. It doesn't. It adds to the beauty. So there's the colors of the rainbow there on the book as well.
Yeah, I found that quite lovely. The book is a delight. It's a quick read. I actually, because I don't think it's available yet on audiobook format, I actually put it into an app called Speechify, and I listened to a British accent voice, and it was really delightful. This book can be consumed with delight in just a few hours. And yes, those characters speak vividly through the book. As well as some of their maybe counterpoints. And maybe I want to start with the epic battle between Walt Whitman and Richard Feynman, the learned astronomer versus the learned physicist. And of course, Feynman, as you quote, says, do I care less about Jupiter because I know he's not a god and made of methane? No. So I taught a class here with a Pulitzer Prize winner by the name of Ray Armantrout, who's a poet. And we taught a class called Poetry for Physicists, which is the exact opposite of what you normally teach. But I wonder how much can we learn from our poetic friends? As your countryman Paul Dirac said, something like, poets attempt to explain the most simple things in the most obtuse obfuscational language possible, and in science, the joy is doing just the opposite. So explain that tension, that fundamental tension.
I don't see that tension. I start off in the book and saying, first of all, science isn't a collection of facts. That's called knowledge. Science is the process by which we acquire that knowledge. But I also acknowledge that there are other ways that we gain knowledge, enlightenment, and wisdom. And it could be through poetry or art or literature or music or contemplation or religious texts or just discussing and debating with our fellow human beings. Science is one way. And when it comes to the natural sciences, our area, physics, for example, science, I believe, is the most reliable way of getting to understand the nature of physical reality out there. Poetry is a tool that can bring that to life, can add to the narrative, to add to the story of how the way the world is. I don't think poetry detracts from our ability to understand. I think it enriches in the way that science also enriches our understanding. So different ways of looking at the world.
Yeah, hopefully they can complement each other and not
Absolutely.
lead to some further warfare. So you mentioned knowledge, and of course the word science in Latin means scientia, means knowledge, but it doesn't mean wisdom. That's what sapient or sapienza means. So do you think at some level enough knowledge can kind of convert you to having wisdom? In other words, is there a quantity after which you assume such amount of quantity of knowledge that you actually become wise? Or are they fundamentally blocked off from one another?
I don't think they're the same thing. I mean, that they are connected with each other. The more knowledge and experience you have, I would suggest they're correlated. You should be more rather than less wise. But I don't think wisdom is something that can be acquired. If someone who knows nothing about a particular area or discipline, if they could absorb all the knowledge and information about that discipline, that doesn't make them wise. I like the fact that for me at my stage in my career, I'm now leaning more towards offering wisdom to my young students rather than the knowledge. They're smarter, they're faster than me, they can remember stuff. I've forgotten more than they've learned, but I hope that I can offer wisdom. And I don't think that's the same thing as because I have an accumulation of knowledge, but they are connected. They are connected.
Yeah. How do you react to this statement? I'm gonna drop on you. Follow the science. What does that mean to you?
Oh, God. Yeah, it's the phrase that has been used by politicians, particularly during the pandemic over the last 2 years, to somehow absolve themselves of any responsibility, if they don't follow sensible policies. Just to say we are following the science is meaningless. I mean, you say we are following the advice of scientists based on our current understanding. Fine, but if that's what they mean and they've just shortened it down to follow the science, 3 words, fine. But I worry that politicians don't actually understand what is the science. Following the science means doing science, means following the scientific method. You're not doing that. You're listening to someone giving you advice, which chances are you're going to ignore.
In your opinion, I always get kind of reaction to this, that there is no real one scientific method. I mean, you don't go down and, I don't go down to my laboratory and say, now I'm going to test the hypothesis and then I'm going to acquire. And actually there, in my estimation, I mean, you're far better qualified to answer, but there's multiple scientific methods. There's deductive, there's inductive. What is this? What is the scientific method? Is it just a rubric? Is it just a shorthand, or is it a shibboleth? What is it exactly?
I certainly think it's a collection of all the ways that we've used across the disciplines that we call scientific disciplines to gain more knowledge. It's certainly not a box ticking exercise. And say, what does it mean to be a scientist? Well, you have to be curious about the world. Well, a conspiracy theorist is curious. It's about gathering evidence. And well, the conspiracy theorist thinks they're being rational and gathering evidence and being skeptical and so on. Is it about testing a hypothesis against, you come up with a narrative, a hypothesis, test it against observation? Well, a historian does that as well. Does that mean history is part of science? No, it means they're using the same techniques to learn something about the nature of the past as opposed to the nature of physical reality around us. So there isn't a list of things. Yes, some areas of science require, falsifiability or reproducibility and so on. Other areas require testing of hypotheses and coming up with a theory that has predictive power. But even, having predictive power is not enough. Your star signs, reading your astrological star chart may say you're going to get promotion next Tuesday when you're going to work. And sure enough, your boss gives you a promotion. You say, oh, look, it predicted correctly. Therefore, astrology is a science. But, there isn't one size fits all. It is you're right. It's a nebulous term that can mean different things depending on the sort of science that we're doing.
My thumb is very busy right now holding up good old Albert, but if yours is free, please go ahead and hit that like button. And don't forget to subscribe. It really helps us with the algorithm.
So last year, past guest on the show, Lord Martin Rees, told me, pertinent to astrology, that, he's responsible as the astronomer royal to tell the queen her horoscope. I thought that was really nice. I'd like to have that gig, for the president here. I'd like to be the federal astronomer.
Yes.
But in reality, there is, as we maybe pivot to a subject that you bring up in The Joy of Science, this kind of fascination with Karl Popper and this falsification. And you just pointed out, not only could such a prediction of a soothsayer, as Popper called them, come true, but it's also falsifiable. If you didn't get the raise, so then his hypothesis was falsified. Therefore, it's science. What gives? I mean, how much should we put on Popper? I mean, in my understanding, he didn't even think we should put that much emphasis on falsification as the sine qua non.
No, absolutely. Now, I think when I was a student, it was always argued that the great philosophers of science of our age were Karl Popper and Thomas Kuhn. The paradigm shift ideas. I think these days this notion, that Popper's idea of falsification, isn't held in such high regard, put on a pedestal like it used to. We're much more careful now talking about being good Bayesians. That having priors, what's the probability that this idea is right? Well, based on what your initial assumptions were, surely, and what's the probability that they were right? The idea of falsification, I'd use the example in the book, which is that many people have used before. All swans are white. You see one brown swan, and you say, see, that suggests that it falsifies your theory that all swans are white. But then, how do you know that brown swan isn't just a white swan caked in mud? So the falsifying counterexample itself may not be correct. And we've seen this in physics. The famous experiment of the faster than light neutrinos a few years ago.
Yes, opera.
Yeah, the opera experiment. They detected these particles that looked like they were getting from A to B faster than the speed of light. Oh, Einstein's wrong. But it turns out the experiment itself was wrong. There was a loose cable behind one of the counters in the computer. So
that's right.
Just having one so falsification is probably not as a strong a definition of what a good scientific theory should be.
And then you mentioned, a frequent character in all popular books, in addition to Feynman and Galileo and Newton. You mentioned Einstein just a second ago. And chapter 5 in this wonderful book is called entitled "Don't Value Opinion Over Evidence." And I wonder if we could talk about authority. And my favorite scientist of all time is Galileo, who said, in matters of science, the issues of authority cannot overcome the humble reasoning of a lone individual. Of course, I get that all the time. Yesterday alone, I posted on my Twitter, I'm going to be talking to you. And I got all sorts of questions, like people wanted me to ask you about their theories about, conscious electrons and this thing. And we'll get to some audience questions. Don't worry, because that is part of my hallmark on this channel. But nevertheless, you should also have some respect for authority in science. As Feynman or Sagan, I can never remember which one, said, I'd rather have, answers questions that cannot be answered than answers that cannot be questioned. To me, that's a canard against religion. But I wonder, do we worship this guy a little bit over much? Are we kind of infatuated? In fact, in the public, when we see things like during the coronavirus that you just mentioned, or with the Iran nuclear deal, they trot out 70 Nobel Prize winners, 11 of whom have been on my show, and they'll just trot them out. And then we're supposed to say, okay, we'll just do what you say in all these matters, even though you're a condensed matter physicist talking about a vaccine that's, mRNA. Anyway, to what level should the general layperson experience a little bit of the joy of science by questioning the authorities, even this guy?
First of all, having is something we see on social media more and more these days. Valuing opinion over evidence is a worry, and it's true that when my plumber comes around to fix my boiler and he says, "Oh, I know what's wrong with it. There's this error. It means you got to change the circuit board." I don't say to him, "Don't worry. I've had a look on YouTube. I know exactly what's. I can do it myself."
Or I'm a theoretical physicist.
I'm a theoretical physicist. Everything is made of quarks. Surely I must be able to figure. I know so much more than you could ever. No,
because Lenny Susskind was a plumber, so.
Oh well, right. Okay,
Well,
so yeah, well,
theoretically.
so he can do that. He can say that, but the rest of us no. So to some extent, you have to say, look, someone has expertise because they've had years of study and thinking about this, and you can't just come to it and say, what right does this person have to say that they're right and I'm wrong? I'm sure you get the same as me. We get the emails and the letters from people saying, I have no background in physics. However, I've proven Einstein wrong. E equals mc cubed, not mc squared.
And if you help me, I'll share the Nobel Prize with you.
Yeah, but I'm not telling you yet because that's right. You have to help me get my stuff up. I think, so you don't want to insult people. Some of these people are very earnest and genuine, and they've spent years thinking about this stuff, but they haven't had the benefit of doing a proper course in physics, for example, relativity theory. And in all likelihood, you have to tell them, look. Just because no one believed Einstein when he came along, and he changed caused the paradigm shift, doesn't mean that you are also another Einstein. With all
That
due
syllogism
respect,
doesn't hold, right?
yeah, with all due respect, that he was one of a kind. But you're right. The flip side is that we overly respect someone because they have a title or because they have expertise in one area, and we assume if it has the whiff of science, then it must be true. I mean, in the commercial world, in businesses, this is how they advertise stuff. You add a new yogurt or a new face cream, you add a scientific word there, and see, scientists have said, and therefore it becomes the truth. So we do have to question where the evidence comes. So chances are, if someone's dedicated their life to a subject, then I would give them the benefit of the doubt. I wouldn't assume that I shouldn't trust anything they say because they may have ulterior motives. They may have ulterior motives. They may be saying something because their paymasters want them to, or because they want to promote a particular theory because they've invested their lives in it, even though it's wrong. But there's a good chance that if you're an expert, you probably know more than someone who just comes up with some opinion.
Do you think you can, turn someone into a scientist, just based on their pure passion? Like you said, curiosity, I'm curious about conspiracies myself sometimes. We'll get to those later in the next interview. But can you really convert, teach someone to be a scientist? Can you start and if so, how do you do that?
Well, yeah, absolutely you can. I mean, being a scientist, we are not a separate species from the rest of humankind. We are people who, we're all curious as children, and we ask the why questions. Most people, as they grow up, they got to get on with their lives. They got to get a job and a mortgage and a family and all the challenges of daily life. And they stop asking those why questions. They stop being curious about how and why is the world the way it is. They don't have that luxury. Those of us who are trained in science, it becomes our job to keep asking those questions. So we remain curious. But training someone to become a scientist is nothing special. It's about showing how we do science. It's about, the scientific method. Being, some of the most important things are never being completely certain about something, always allowing a place for doubts to change your mind, and also being prepared to admit when you're wrong. And I always say that's the difference between a good scientific theory and a conspiracy theory. Ask a conspiracy theorist, what evidence would it take for me to persuade you to change your mind? And they would have to admit nothing. Nothing would. By definition, a conspiracy theorist, that's their whole reason for believing what they believe, because nothing is going to dissuade it. Whereas a good scientist, has to be prepared to say, I was wrong. I thought this theory, this hypothesis, I could explain this phenomenon. You've presented me with data or some observational evidence that suggests I'm wrong. I have to change my mind. Not all scientists do that, right? Not all scientists are good, but that's the way it should work. And I don't see any reason why anyone couldn't learn to think in that way.
Now, when you hear things like trust the science, I want to pivot now to actually what I understand is the impetus for writing the book. It came out of the COVID pandemic. COVID came out. I recall things in the UK, Professor Ferguson, the rival institution, and other coming out with models predicting dire, numbers of deaths, in a very short period of time. And eventually, maybe that'll prove to be correct. And similarly, you mentioned global climate change and global warming. A lot of this is based on extremely complex physics. And if at all, if it is linear, if we can actually be reductionist and say that, well, a virus is just biology, biology is just chemistry, chemistry is just cell, physics, et cetera, et cetera. At some level, physicists should be able to do stuff. And yet we get a lot of things wrong when we turn to models. Talk about like, what is the role of a model in science, and not the runway kind of which you certainly could be.
One of the guests I'd have a radio show on the BBC, the Life Scientific, which has been going for many years, in which I interview other scientists. I remember interviewing a climatologist, Tamsin Edwards, very smart scientist who works on mathematical models, and she has a website and a blog which has the title "All Models Are Wrong." I forget where the quote comes from. All models are wrong, but some are more useful than others, right, or something like that. So a model is a model. It makes a prediction, and it's only as good as whatever information you feed it in the first place. We try and develop our models to make them more and more sophisticated. We trust models more if you have two very different computational models, two different sort of imaginary pictures of reality that make the same predictions. If they come at some prediction about how something will change and evolve, like what the climate will look like 50 years from now, and they have different assumptions and inputs, and yet both point to the same thing happening, tends to make them, it's a bit like doing two different experiments in two different labs and they both discover the same phenomenon, that reproducibility. So a computational model is like doing an experiment in the lab, but with zeros and ones. And you can get it wrong in the same way that you can get your experiment wrong. So models are useful, but we shouldn't trust that they are telling us the truth. But at the same time, we shouldn't dismiss them out of hand simply because one day we might find that they're incomplete.
And I think that's all well and good when you're looking at, the millennium simulation of structure formation in the early universe, or you're looking at, how certain, primates, evolved and got out of Africa. But, on the other hand, when it impacts, the layperson in their daily life, things like climate change, things like viral, epidemiology.
Yeah.
If you can't trust these people who, as you say, rightfully so, have dedicated their lives to this career, I mean, what does it do to the scientific confidence, people having confidence in science, when they will, if anything, know when people get models wrong rather than right?
Yeah, I think for one thing is people need to understand how science works. And that's something that has happened to some extent over the course of the last 2 years of the pandemic. People have seen the scientific method in action, and have seen these modelers saying, this is going to happen, or, the way to stop yourself from catching COVID is to wash your hands. I don't know if this was the same thing in the US, but in the UK, there was the mantra, wash your hands while singing happy birthday twice through, right? That length of time, And then, a few months later, it was, oh, no, washing your hands isn't so important. You've got to wear a mask, or you've got to have ventilation. And so people who don't understand how science works said, hang on, you guys just told me that I could avoid catching COVID washing my hands. Now you're saying I've got to wear a mask. You know nothing. But if people understand how science works, they say, well, no, this is in the light of new evidence. We need to be able to backtrack, to change our minds, to revise our view. What also is important, particularly for something like climate change, I think, is that we have to apply the precautionary principle, that we know we're never going to be sure that the climate is going to change in this way, or that it's going to lead to these dire consequences. But in all likelihood, it's going. There's the famous example that 97% of climatologists say we humans are changing the climate. There must have been some survey some years ago that 97% of and then people say, well, hang on a minute. So you're not sure. So there's 3% of good scientists who argue the difference. Maybe you're wrong. But if you go to your doctor and your doctor says, if you don't give up drinking and smoking and change your diet, you're going to be dead in 5 years. And you say, well, doctor, how sure are you? Well, I can't be sure. I'd say 97% sure. You're not going to turn around and say, okay, I'm going to seek a second opinion because you're not sure. You adopt the precautionary principle and say, chances are you're right. Better safe than sorry. We should do something about it. And that's how I feel about climate change. Chances are things are going badly wrong, and we need to do something about it. Maybe we don't have to, but we can't afford not to do something.
Yeah, one of the powerful takeaways, from the book and from, conversations I've heard on the Life Scientific and elsewhere, is that, when you say something, when a scientist says, I don't know, it doesn't mean like everything's equally likely. It doesn't mean like, I don't know what's going to happen with, it doesn't mean like COVID's nothing or it's everything or climate change. And yet again, when it does impact, the ordinary person, I feel like you and I just want to toot our own horns for a second. We get paid by the taxpayer at some level to do a job we would do for free. I mean, don't
Right.
tell Gavin Newsom, my
No.
boss, but I would do it for free, right? I don't know about you,
Yeah,
but
yeah.
I assume that you would, because you have so much joy, literally. And that's the reason I think you use that in the title, right? So it's pleasurable. We get paid. So on what other job, if you are the plumber and you come over to fix the house, and the plumber tells you, you can't understand what I'm doing. It's very complicated. And she's right. She's actually very astute and knows plumbing. She's dedicated her whole life to plumbing, as you said. But yet, if she tells you, you can't understand it, it's very complicated. And as you quote Feynman saying in the book, if I could explain why I won the Nobel Prize, it wouldn't be worth a Nobel Prize. On another day, he said, if you can't explain it to your grandmother, you don't understand it. It's like, which is it, Feynman? I want to ask. But anyway, to what extent do you believe, or maybe disagree? I'll state what I believe. I think it's a moral obligation that we scientists have, and that we fail miserably at half the time because we're so busy. But we have to tell the public in terms they can understand, what we're doing with their money that they've given us, this treasure to do what we would do for free. How have you utilized, because you obviously are one of the master communicators who've ever lived. I mean, actually, because of your huge impact, BBC and in America and Netflix and all the places, you've had an outsized impact. Did you have training? What is your underlying philosophy of doing that essential outreach, which is to the benefit of science, so we can keep getting funds to do what we love?
I have to say, in all honesty, I don't do my science communication altruistically because I feel I have a moral obligation for the world to be more scientifically literate. I do it because it gives me joy. I've always said that I don't want just to be a science communicator talking about other people doing the science. I want to be a scientist who communicates. But when I find out something fascinating about the world, why wouldn't I want to shout it from the rooftops? Why wouldn't I want to tell everyone about it? When I communicate science, when I'm explaining something to someone who doesn't have the background expertise, they're not dumber than me. This idea that we said we are dumbing down in order for people to understand, that's nonsense. They're not dumber than me. They just haven't had the benefit of years of dedicated thinking about this stuff that I have. Getting an idea across in a way that I think they can understand. Sure, I'm going to probably I'll be leaving out some of the details of the algebraic derivation that are not important in getting the concept across. But it gives me genuine pleasure to see that penny drop, the light bulb come, and we say, oh, I see now. I get the same sort of tingle, enjoyment of someone understanding something that I've explained that I got when I first learned about that. So I do my science communication because I enjoy it personally. Although, of course, I acknowledge you're right. We have a moral obligation. Not every scientist is good at communicating science. Some scientists in academia are better at research. Others are better at teaching. Horses for courses. But those who can communicate, those who want to, like you and me, who want to sort of get across these ideas and empower society and enthuse, absolutely we have to do it, because that's, this is not something that we should be keeping to ourselves.
No, it's too much fun.
Yeah.
It's magic that's real, right?
Yeah, right.
I want to ask you, what's the biggest source of hype right now in physics or science in general? What is the biggest, perhaps most overblown thing in science that's falls in the category of hype?
I think it might be when we talk about the opportunities with quantum technologies and quantum computing, for example. The impression that the public gets is that quantum computers are going to replace our current computers, and they can do everything so much quicker and better. The same with artificial intelligence, that we are years, maybe decades, but maybe only just years away from artificial general intelligence and machines that can become conscious. That sort of hype, I can understand why, because they're exciting, and Hollywood makes a good living out of the science fiction movies that based on those themes. But it does give people the wrong impression that we're approaching this wonderful, these technologies that are probably we're not going to see in our lifetime.
All right.
In a few decades ago, there was a lot of hype in theoretical physics that we were coming to the end of theoretical physics, that the Large Hadron Collider would discover all sorts of new particles, that that we were approaching a theory of everything. And Stephen Hawking wrote an article about 40 years ago about, the end of theoretical physics. Just got to dot the I's, cross the T's. And no, actually, we're a long way off. We don't even know what dark matter is made of. Right? So there was that hype. I think we've sort of sobered up a bit from that. We realize we have a long way to go in understanding the nature of reality. But in the technologies that are being promised now, I think that there's a good deal of hype that we should also try and pull back from.
Funny that you mentioned it, because we did talk about that, and it's sort of like what I say about string theory. String theory is the best theory ever made to describe the properties and possibilities of string theory. And it seems like quantum computers are really good, as Feynman predicted, at like unraveling how quantum computers work and how Lagrangians work. But in my field, of cosmology, we hear about the multiverse. I even had on David Chalmers talk about the simulation hypothesis. Are these things that physicists use to generate, clicks and eyeball? I certainly do that, by the way. I mean, this episode will be called, Jim Al-Khalili tells all, in a way that he's never told it before. COVID free and loving it. COVID was a 5G ruse. No, I'm not going to do that. Don't worry. But in reality, we kind of do, there's a universe running backwards in time. I just saw in The Guardian last week. To what extent does that, is that playful? It's in good fun. Or can it really detract from the public support? They find out like, well, didn't you guys claim neutrinos travel faster than the speed of light? That appeared on page 1 of the New York Times. But the retraction appears on page, this B17 on the weekend edition 6 months later. So what responsibility do we have? I've said we should have a PR budget. I'm fully aware we should have a PR, but we should have a retraction budget as well. Like, how do you deal with the self-correcting essence of science, which you touch upon so heavily in this book? Science is self-correcting. It's often wrong. Never in doubt, maybe, but how do we correct in a way that shows the public that we're honest, have integrity, but we also make mistakes?
It's difficult when it comes to subjects that, the sexier parts of science, things like, the cosmology or particle physics or advances in genetics or artificial intelligence, because, the media and journalists, even if they're good science journalists, they want the headlines, they want the clicks, they want to enthuse, and they don't care if, as you say, a month or two down the line, it turns out that was just wrong. It's too late. You've got people excited. In some respects, I think it's good to enthuse the wider public with the excitement of science. It happened back in 2008 when the Large Hadron Collider was turned on, and in the run up to it, people say, "Oh, you turn on this particle accelerator, so much energy, you're going to create a black hole that's going to swallow up the Earth." And a lot of my colleagues were horrified by that. That's bad science. Well, yeah, it's bad science, but you got people in bars talking about particle physics, and but you then have to follow it up. Right, you have to follow up to make sure that people's expectations of what science is going to deliver are realistic. These are exciting things. They're fizzing our imagination, but that doesn't necessarily mean that they are correct. Because you're right, because then if a few months down the line, say, oh no, we thought there was inflation and there isn't, or we thought there were parallel universes. And well, what do we believe? So we've got to explaining the excitement and the coolness of some of the science that we do. We also have to explain how we do science. Part of that is to say that, look, this is a hypothesis. We don't know. We haven't tested it. String theory is very neat and powerful maths, but that doesn't mean that, there are 10 dimensions of vibrating strings that may turn out to be wrong. Is it science? Yes, it's still science. Cosmology and multiverse, even if something isn't testable, doesn't mean it's metaphysics or philosophy or theology. It's still part of science. It's just we haven't figured out how to test it yet, right? I'm more optimistic in that way. One day we might be able to say whether string theory is right or wrong, but until then, it's nice maths.
Yeah, and if you say something is settled science, that to me closes off the possibility that a young,
right,
Alberta Einstein or will come along and solve this great problem that you actually were wrong about, but you didn't know it because you felt
that's a much better outcome. We didn't want the Higgs boson to be discovered, right? Because that would have meant new physics to be. Oh, okay, it's there after all. Tick that box.
Yeah, I mean the experimentalists wanted it to be there.
Oh yeah. Listen. If you've spent 20 years building the largest particle accelerator in the world, yeah, you want to find something.
And speaking of which, I'm going to have Frank Close on
Oh,
soon. My
wow.
fellow
Great. A good
countryman. He
friend of
wrote
mine. Yeah.
Yes, he wrote a great new book called Elusive about Peter Higgs, kind of a bio of him, scientific, but also popular bio of him. So one of the delightful chapters that I really loved is entitled, chapter 7 is entitled, Don't Be Afraid to Change Your Mind. I want to ask you, Jim, what have you changed your mind about?
In my area of research, so I started off, I don't work so much in nuclear reaction theory now, but I started my PhD was into studying modeling nuclear reactions. I remember looking at a particular type of atomic nucleus and how the protons and neutrons are arranged. And I had developed a model to calculate cross sections, so the chances that a particle hitting another was going to bounce off at a certain angle. And I developed a model, published papers on it, and then realized that what I was doing wasn't the complete picture. And I remember having a running battle with a rival group of researchers, and so we'd like stand up in conferences and I can ask this question. Why? And I think both of us realized that the other guy was also right, and that somehow we had to find a compromise. And so you do that in science. You have a view, an idea, or you develop a theory. You publish papers. You have to be prepared, to admit at some point that is not, the end of the story, that you may have an incomplete picture. I don't like admitting this, but I hated the many worlds interpretation, the Everett's interpretation of quantum mechanics. One of the ways of explaining, what is going on in the quantum world. I blame, people like Sean Carroll because they are so persuasive.
Yes.
But I have to admit that I'm sort of thinking, yeah, it is quite appealing. I'm not as against many worlds as I used to be, and I'm saying this publicly now, maybe for the first time. So I may live to regret my words. But yeah, you have to be prepared. That's what science is about. It's not about holding on to a cherished idea or view or ideology. That's why it's different from politics or religion or in science. It's about the way the world is, and if someone tells you it's not the way you thought it was, you have to accept that.
So we're coming close to the end of your allotted time, and I have a few more questions for myself that we'll wrap up with. But I want to answer at least a few audience questions, and we're starting with one from a young, very shy, very unknown scientist by the name of Sabina Hassenfelder, who endorsed your book, your lovely book,
Indeed.
blurb, along with, she's a past guest, an upcoming guest for her new book. And then one of my best friends, Sylvester James Gates of Brown University, blurbed it as well. But Sabina asked the following question: what's the most exciting area of physics? So it's kind of the contrappost to the what's the biggest hype. She wants to know, what do you think is the most exciting area of physics or science? It could be all of science.
Well, it depends on what the most exciting area for me, or the most exciting area that I think other people think is.
For you.
For me, well, for me, I mean, when people look for a theory of everything, we're working in quantum gravity, they're trying to unify two of the big pictures in physics. The quantum mechanics that describes the world of the very small, and general relativity describing the world at the cosmic scale. And as we know, they're struggling to find the correct picture, whether it's string theory or loop quantum gravity or some other idea. For me, what is exciting is unifying quantum mechanics with another pillar of physics, which is thermodynamics. So for me, the most exciting thing is this new area of quantum thermodynamics. In quantum information theory, quantum thermodynamics, the far from equilibrium statistical mechanics, all those ideas to do with things like the nature of time itself, I find is the most exciting. Where does the arrow of time come from? Where does the irreversibility of time come from? When down at the quantum world, even and indeed in the Newtonian world, the equations are reversible in time. So where does that direction in time come from? It exists in thermodynamics. It points in the direction of increasing entropy, increasing disorder. How does that link in with quantum mechanics? So for me, what's exciting is trying to blend together, mesh together quantum mechanics and thermodynamics. There are people who've spent years thinking about this. I'm sort of coming to it quite green, but I've bought the textbooks. I've started reading the papers. I've got a couple of postdocs working on it. That's what's giving me a buzz at the moment.
Okay, this is a question from my YouTube channel. So a reminder, you can ask questions of all my guests on my YouTube channel, which is Dr. Brian Keating. And this one is from Nicholas Paulson. It's more of a statement. And he says, don't miss the book called The Science of Joy by Jim's brother, Jim Al-Khalili, not Al-Khalili. I didn't know you had a brother named S.
I didn't know, nor did I know that he'd written a book so similar in title to mine.
And is an alkaline. He's an acid. That's the guy. It's
That's
a joke.
what it
It's
is.
a joke.
Yeah.
So the last question from the audience from my friend who goes by the moniker Memes of Destruction, which I was actually going to choose for one of my kids' names. He says, I keep hearing about an anti-universe. Might this or some hidden phenomenon help explain the similarity between gravity and electromagnetism? Maybe this universe that runs backwards in time, could that somehow explain equational simplicity or similarity between Maxwell's equations and Einstein's equations?
It's difficult to say what is the similarity between Maxwell's equations and Einstein's equations, other than the fact that we can describe them both in terms of fields. We have a gravitational field, we have an electromagnetic field, but the whole difficulty in finding a theory of quantum gravity is unifying quantum field theory, which encompasses the electromagnetic force, with general relativity, which is gravity. So the problem in modern physics is how gravity and electromagnetism come together. Now, Einstein was working towards this, but he wasn't doing it at a quantum level. The idea that there are ideas back in the early 20th century due to Kaluza and Klein suggesting that there is a connection between gravity and electromagnetism, and you need another dimension to bring them together. But the notion that an anti-universe, I don't even know what an anti-universe means. Is it a universe made of antimatter, or is it a universe running backwards in time? They're interesting ideas, but I think it's that there are too many concepts that we're trying to sort of put together logically here to make any sense of.
Well, Jim, we've reached the regularly scheduled question limit, and now we're going to break here. Going to create a separate video where Jim is going to answer the patented thrilling three questions about existential meaning and wisdom. So you'll have to subscribe to the channel and over on my newsletter at briankeating.com to get that. I'll have links to Jim's phenomenal output and all of his TV specials and, of course, the Life Scientific. Jim, thank you so much. And please stick around for a few more minutes of existential questions.
My pleasure. It's been fun.
Okay.